Welcome back, chemistry fans. Today is topic 13. Oh, sorry, unit 13, topic 1. We're going to talk about acids and base. Let's jump right into the subject matter. This is going to be kind of quick because of the time frame where we are in the school year, but I think that a lot of this you will find vaguely familiar from just everyday life, not even stuff that we have talked about, but just from your daily experiences with some of the stuff that you eat, consume, and use to clean with. So acids is this first topic. We got to be able to describe what they are. If we think about what acids are in the Hollywood sense, well, they're these very dangerous materials that if you were to utilize them, they would destroy whatever they touched. And you can see that in Breaking Bad, where his partner has to dispose of some weapons, and so he pours acid on top of them and dissolves through not only the weapons, the items, but it also dissolves the bathtub and parts of the house. And that's not necessarily true. Yes, dangerous is an acid, but it doesn't have the capacity to continue to eat through all types of materials. It wants to eat through specific ones. So we need to understand this. Acids generally only like to dissolve metals. They have a tendency to then also corrode some organic materials, but they don't have a real strong effect on our plastics, or if we are going to talk about ceramics. They just tend to not want to eat away at those. Those have protective barriers. So what makes you an acid? We need to understand that the letter H is significant, both for acids and bases, but for specifically acids, you will notice in the formulas, the first letter will be H. If you see that, you know it's an acid. You may be asking yourself, though, but what about that water on top of the arrow? That's also got an H at the beginning. Well, that's because it is 1/2 acid and 1/2 base. Water is made up of H and OH. If you have 2 H's and 1 O, that's water. So 1/2 of water is acid, 1/2 is base, and that's why it has a pH of 7. It's neutral. Some other properties of acid is that it has a sour taste. It tends to conduct electricity, reacts with metal. It has a pH less than 7, and it tends to be some kind of a sticky material when it dries up. It is, as it says, low on the pH scale. Unfortunately, this pH scale is in reverse, but what you can notice, some things that are acidic, any of your fruits, vinegars, your stomach acid, as well as the acid that is in the batteries that helps conduct electricity. Now, bases on the other side are, generally speaking, anything that you use that is a cleaning material. So they are caustic, is the word to describe that, and they neutralize bases. They tend to work on organic materials where acids are not as effective. So bases, just as dangerous is the big picture, and they end with the letter H. They don't begin with the letter H, they end with OH, specifically hydroxides. So that's how we can determine them. Some of their properties is that they have a horrible, bitter taste. They will feel somewhat slimy, just like all of your cleaning supplies were, and they are high on the pH scale. So they are pH 7 or higher. So where you see down here some of those materials, your antacids, makes sense, and your soaps, your bleaches, your drain cleaners, dangerous materials. All right, so there they are in comparisons. Acid begins with H, bases end with OH. So here are some terms, though, that could pop up on the AP exam. Not going to be on our quizzes more than likely, but could pop up as something in context for a question. They are amphiprotic and amphoteric. Both words sound very very similar, and that's on purpose because what they mean is that both materials act as acid, and one material that can act as both an acid and a base. So amphoteric over here on the right, those are in purple hues, they are an acid and a base. Amphiprotic are materials that donate H's and accept H's. So all materials that give away H's and accept H's are acid and base. But not all acids and bases give and accept OHs. So there are some subtle differences that we need to understand, but I wouldn't put a whole lot of time in trying to distinguish betwixt the two. What we need to know is if we see that amphi word or amph portion of it, what that means is it does both. So here's an example of the amphiprotic. So in this example, the HCO3, notice that it could accept a hydrogen and become H2CO3. So accepting an H, or it could donate an H. So in this case, it donated the H. It left off an H. In the other case, it accepted the H. So amphiprotic means either accepting or donating H's. That means that this HCO3 is both an acid as well as a base. Not amphiprotic, but amphoteric. This is amphoteric. Amphoteric in this example is the water. The water is acting as both an acid and a base. In this case, the hydrogen leaves the water. It donates the H, and that makes it an acid. But in the other example, it's acting as a base. It is stealing the hydrogen. The hydrogen is being added to it, and therefore it is acting as a base. It is accepting the hydrogen. All right, another term that may pop up is a ligand. Now, in biology, they pronounce this as a ligand, but in chemistry, we pronounce it as a ligand, and it's the same word and it has a similar meaning, but in chemistry, what we are talking about is any material, any ion or molecule that can donate electrons. In other words, it's a place where you can form a bond. That's what we're talking about. It's a place where you can form a bond. So here's some examples of ligands. What you will see here is ligands are these places where we have these extra electrons. So if we needed to count how many ligands there are, we just simply need to look for where those pairs of hydrogens are, or of electrons, where the pairs of electrons are. When we see that pair of electrons, that's a place where a metal can come in and attach itself. That's a ligand. All right, last terms that we need to deal with are monoprotic, diprotic, and triprotic. Now, summing up the di and the tri, you could call those polyprotic, meaning many protic. Now, what does protic mean? Protic means hydrogen ions. So what we're talking about is down here. If you are monoprotic, you have one hydrogen ion. And why would that be? Because hydrogen is made up of one proton and one electron. Well, if you lose the electron, all you are is just a proton. So monoprotic means one proton, diprotic means two protons, two hydrogen ions, triprotic means three hydrogen ions, three protons. Generally speaking, the more protons, the more hydrogens you have, the stronger you are as an acid. Now, not always the case, but generally speaking, the more hydrogens you have, the stronger the acid, the more dangerous it is. So again, if we are looking, this is H2, H2, H3, but over here, notice only one H in each. Monoprotic versus polyprotics. All right, now we're into the classification. There are three ways in which you can classify an acid. The Arrhenius acid means that you donate an H. Well, the Bronsted-Lowry, it kind of says the same thing. It says you donate a proton. Well, what is a hydrogen ion? It's a proton, so it's the exact same definition. They both donate hydrogen ions. And then the Lewis acid, it focuses on those ligands. It says that there is a place for us to have a material bond. So we're looking for electrons, is where we can see somewhere that is accepting of electrons. That's where we're going to call the acid. All right, so in more detail, here's Arrhenius acids and bases. So the Arrhenius acid gives away an H. It releases that H. But on the other side, the Arrhenius base releases an OH. So now this is the classic definition. Started the discussion of acids and bases. If you begin with the letter H, you're an acid. If you end with the letters OH, you are a base. That's what Arrhenius acids is telling us. But there's a problem with this. There exists a molecule out there, NH3. You would say, oh, that's an acid because it has an H. However, it is a base. And so that's the reason why the Arrhenius concept does not work fully. So they had to come up with a second method to explain it. And so that's where Bronsted-Lowry comes in. In the Bronsted-Lowry, what we focus on for the acids is the same thing. The acid will donate a hydrogen, where the bases are going to accept the hydrogen. That hydrogen is donated if you're an acid. It is accepted if you are a base. So the definition of the acid did not change. The definition of the base did change. The base is now focused on where did the hydrogen go. If you donate a hydrogen, the other one needs to accept it. So that's where we now have our focus. Acids always donate hydrogens. The bases are going to accept them. The limit on this one, there are a few times, though, where it breaks down. In some of these hydroxides, we have scenarios where we are not going to fully donate. We have OHs, we don't have Hs. And so they're not going to be willing to accept an H. However, those are bases. So they had to come up with a third, more functional, which is the ultimate correct model. It's called the Lewis structure. And what we focus on instead of hydrogens, instead of hydroxides, OHs, we focus on the electrons. So what you will see is that the acid, instead of donating hydrogens, what we focus on is that the acid accepts electrons. In exchange for giving away your hydrogen, you are accepting electrons. The base is the opposite. The base is going to donate the electrons. So the good news is the Lewis model does not come up on the AP test, so I will not be testing you on that. I'm just making you aware that there is a third version of it. Now, how do we lose electrons? How do we lose these hydrogens? It's through the process of dissociation. We have talked about this before whenever we talked about solvation and how materials dissolve. What we need to know is that whenever an ionic material gets into water, it will separate into individual ions, individual positives and individual negatives. Those are called, or that process is called dissociation. Now, how does that affect us? Let me remind you, whenever we're dealing with compounds and we want to be able to write out how they are dissociating as an acid. So this HCl is going to break apart into one hydrogen ion and one chlorine ion. The H2SO4 is going to break apart into two hydrogen ions because there are two hydrogens. So it does not break apart into H2 because that is not an ion, that is a molecule. It does break apart into sulfate, which is a polyatomic ion. Now, for the bases, same thing. It will break apart into an ion positive and an ion that is negative. The aluminum hydroxide breaks apart into a +3 and it breaks apart into 3 OHs that are negative. Okay. This is everything that I wish to, oh, sorry, no, there's 2 more things. I was close. The acid-base indicators. So how do we know physically? How can we see a difference between an acid and a base? Because all acids and bases look the same color. They're both clear for the most part. How would we know if we have a difference in one? Well, we have an ability to mix it with a chemical and it will change colors. It changes colors whenever it has reached a specific pH on the scale. So what you will see here is that if I wanted to find some material that is a pH of 7, what I could do is I could use bromothol blue. And what will happen is it will go from yellow and it will turn blue when it hits a pH of 7. Well, what if I had a material that I wanted to know the pH was 2? Well, I could use thymol blue. When it goes from red to yellow, I know that we have hit that target range of pH 2. All right, now I'm on to my last pieces of the puzzle. Going along with dissociation is neutralization. It is a double replacement reaction where we have an acid and a base, and it will always, because the acid is H, the base is OH, it will always make water. The salt does not always make NaCl. That's not the case. It's a salt is a generic term meaning a metal and a non-metal added together, but it's a double replacement reaction always. What it forms is something called a conjugate pair. The acid, remember, it gives away its H. If it is an acid on the reactant side, it becomes a base on the product side, because what is this acid particle looking for? Well, it's looking for an H. So that H could come right back over here. So it is called a base because it wants to accept the hydrogen, just the same O's over here. This hydrogen is going to bond with the base. The definition of an acid is donating a hydrogen. The definition of a base is accepting the hydrogen. So we see consistency. It's just that they're on different sides. Acid makes a base. The base makes an acid. And this is called a conjugate pair. The conjugate pair is on the left side, it's an acid. On the right side, it will be a base. If it's a base on the left side, it will make an acid on the right side. And on the right side, they're always called conjugate acid, conjugate base. So here's a real life example. So what you notice on the left, it has its H that it's going to give away. It no longer has that H. So when it's an acid over here, it's a base over here. How do I know it's an acid? Because it's going to give away that H. You notice it's missing over here. If it's missing, that means it was the acid. But this base, it took the H and added it. So now it went from 2 to 3. It added. So the base became an acid, and the acid became a base. Now, one of the other sides of this that we will talk about later is that if it's strong on one side, it becomes weak on the other. So if you are a strong acid, you will become a strong base. If you are a strong base, you will become a strong acid, and vice versa. If you're a weak acid, become a strong base. They reverse whenever they go over to the other side. All right, this is now finally everything that I did wish to share with you about topic 1. Thank you very much. I'll talk to you again soon. Bye-bye.